Alors, attends, qu'est-ce que c'est ça? So, dear Catherine, this is a pleasure to see you again in your initial places.
Yes. So thank you, Paul, to give me the occasion to speak again in the room where I defended my PhD. So it's less place, less stress. Thank you very much, Paul. And I would like to apologize because I thought I have something new to tell you from September, and something new just said. So it's something not new. It is mostly the same thing that I think not everybody was there in September. So everybody. But I'm going to say other things, but mostly the same. So I'm going to speak about local convex fuel. How with local convex fuel you can recognize the support of density, and you can recognize the level set of the density. And for ecologists, the vocabulary is for the support, it's a home range, and for the level set, it's a core area with beautiful accent. So that's that. What is it about? It is about statistics. Absolutely not. My theorems are not dependent, but the new thing in this presentation with regard to September, that I'm going to give some keys of how the proof works, and so maybe you can see if it can adapt to a dependency or not. Clearly, it comes from a paper in ecology, so it's clearly applicable. And unfortunately, it doesn't deal so much with networks. So what the original idea? The original idea was in a paper in ecography, and where an algorithm is proposed, and just proposed like that. There is afterwards there is a lot of things like that, but everything they say, okay, we have a set of points of observations, for each observation. Was that? Just kidding. Each observations. This one, I look to its nearest neighbors. We got the convexure of this nearest neighbors. We sort every convexure by decreasing volume, and then we plot them again, starting with the convexure with the highest volume, with a very clear level of gray, and then you have the second convexure with the second biggest, largest volume, with a gray a little bit more dark and more dark and more dark, and you do this plot. And that gives you a representation of the core area. So I'm going to go very far. Thank you.
Comment on fait? Je pense qu'il faut aller ailleurs.
Je pense aussi.
Peut-être là. Essayez de voir si là ça marche.
Non.
Là, je fais. Mais je ne sais pas si je suis au bon endroit. Je crois pas. Attends, on va quitter le mode. Sorry. Let's do this. Let's. Okay, wait. We shall do it. You know, the thing is. So here you can do it. No? No? Okay.
And yeah. Okay, I can do that.
Yeah, okay.
Okay.
Yes, wait, I have to. Attends, il faut que je ressorte du mode mon écran. Parce qu'il faut repartager maintenant. Voilà. Est-ce que là, ça marche ou pas le truc? Non, donc fais-le avec.
Ouais, je vais faire avec ça. Okay, so no, it's great, but the idea is you select this point, its nearest neighbor, you draw the convection, and then you put this one with lighter gray, this one, and you start with the highest one, and here I do something. Hop là, tac. And it makes you maps. Okay. Definition is not so good, like that, representing the area of living area of animals, if your points represent location of animals. So let's go back. So if we want to study this algorithm, to translate what is proposed into mathematics, there's something back to work. It means that you estimate the support as the union on all the observation of the convection of all center observations come after. You estimate the density with this formula, which is, we are going to discuss that after, and you estimate the level set as a set of points where the level set of level t as a set of points where the estimated density is superior to t, which is quite classical, and the density estimator, if I recall that, or big because it is not so bad. So recall what is there. You fix a number of neighbors, k, you say, all right, I'm going to see my k numbers of neighbors, and then you divide k by the number of observations times the volume of the convection, and you take a big max on that. So that's the formal mathematical translation of what is proposed in the original paper in ecology. If you look to these two propositions, this is really very nice. I'm going to speak with this one just after. So this one is really okay. And this one is quite nice. There is a good intuition, but can be corrected and improved to obtain better convergence rates and less bias. And to see why there is bias here, there is twice bias. You can see that the usual estimator, density estimator of this shape would be k m times the volume of ball. So this is when you are inside the support, this is clearly inferior to, you have a ball of Rn. If you look, the volume of the convection is clearly less than the volume of the ball. So when you are deeply inside the support, I don't want to explain that, this is not a good idea with regard to that. But if you are close to the boundary of the support, it's a good idea because when you divide by the volume of the ball, you make an overestimation of the density. So when you are close to the boundary, divide by this is clearly better than divide by this. But still, yes. So you have the problem of the division with the volume here, and also you have the problem of here you have an overestimation, and here you have another overestimation. So we are going to propose a new estimator based on this idea, but with bias correction. So first part of the talk will focus on the support estimator, and second part of the talk will focus on the correction on the density estimation. Okay, that was exactly what I said. To go a bit deeper into the theoretical result, we have to set hypotheses. And the hypothesis is this kind of domain of set estimation, level set estimations, so mostly always the same kind of hypothesis, which is we work on density which are quite similar to uniform density. That is, you have a compact support and big gaps between being in the support or outside the support. The density is bounded below by some positive constant on the support, and you have a cliff. And we will ask our support to be smooth again, smooth enough. And smoothness is usually represented by inside and outside rolling ball conditions, which is expressed here. That means, I think, small plot is better. On each point on the boundary, you can draw an inside ball meeting the boundary at your point, and an outside ball, and you can roll balls inside the support and roll balls outside the support. Very point of that is that it allows you to make a lot of differential geometry without differential geometry. So you can do that up with Pythagora, which is nice because it's clearly easier than differential geometry. It's more formally, it has been proved to be equivalent to the boundary of the support is C11 manifold. It is C1 and C2, C1 plus an initial condition. Okay, that's just to say. And what we are going to do also, it's not exactly what I said before, because it's too complicated. We are not going to work first with nearest neighbors. We are going to work with a fixed radius, a window size fix, and not a number of neighbor fix, which actually makes stuff easy, mostly for the density estimation part. So first of all, how does our support estimator behave? And recall that our support estimator is a union of small convexure of neighbor of each observation. It will behave very well. It's this theorem. It tells you that if you take radius sequences of this order, you can achieve this rate. These rates are the minimax one for and you can also have a nice result if you are interested in geometry. You can say that with probability 1, when n is large enough, your support will be homeomorphic. Your estimated support will be homeomorphic to your initial unknown support, and the same for the boundary. This way is clearly in an independent setting. Here you have an illustration of the kind of maps we can do, which is done points are the CSMs. So I don't know which are from 1 to 1. Just CSM, and in red it's a CSM with magnitude more than 6. So you can do nice plot. What is quite nice is that it fits quite well the fact that you are close to a lower dimensional case too. It's very nice. So this one is a new slide. I wanted to give a points on what are the key points in the demonstration, what are the key points in probabilistic one, so that maybe you can adapt the results in dependency case, because present you for independent case. And you need to control two things. The probability is here, I'm going to explain after. Everything else in the proof is only geometry, and geometry with the relief condition is mostly only Pythagoras. So it looks difficult, but it's not so much. And what are the control stuff? We need first to have control on that. That is that we must find what we call radius rho inside. That says that if I take all the balls of radius rho inside with x in S, all of these balls contain at least one observation. So I need to have a dense enough sample in the support to be able to do something. So I need this to find a suitable rate, and it goes to zero quickly to find something that goes to zero quickly enough to be able to apply while continuing them after. So I put something here that you can find anything that is summable. And so you need to find a rate like that, and then you have also to focus on the boundary. You have to find another rate that are indexed by the boundary. And it's the same thing. It's for given shape to ensure that any given shape ensemble given shape will contain an observation. And this one is related to the boundary, and it's a cylinder. So you need that sort of tangential cylinders meet with probably all the tangential cylinders meet an observation. And the tangential cylinders are like that. You have a red, here are something of a square. If you have that, the choice of the radius with this one will give you an error in convergence rate with a square. And in the IID setting, you can find the integral rate with ln of n on n at the power 1 on d. This is the dimension in which you are. And the boundary one is on 1 on d plus 1, and then u squared. But if you find rate like that, over rates like that, you will have this conclusion with a little bit about. So if you have something with data points that are not independent, try to find something like that. You will win. So now I'm going to talk about the density estimation part. And the density estimation part, it's a bit tricky. It requires a lot of new notations, which are here. So you take a point X, you draw the ball centered at X and the radius are N. This is a number of observations that are within this ball. And you have to consider other points, for the convection. And you also count this indexed by the boundary, which are the vertex of the convection of your observation within the small balls. And the points which are, you also count the points that are inside the convection. And the density estimator that we can propose is this one. So, what is it? Instead of counting the number of points that are in the ball, you count the number of points that are inside the convection. You divide not by the total sample size, but by the total sample size minus the number of vertex of the boundary. And then you apply the volume of the convection. You have to add a lot of indicators just to avoid dividing by 0. So you have to guarantee that the volume of your convection is large enough, and that you have not too many points in the boundary. This one is mostly obvious. The problem here is here. If we worked with nearest neighbor, we won't have that, but we have no problems. And this one has a very nice result. So with the same hypothesis that for the support, adding also that the density is a plus C2 on the support. Otherwise, we have this kind of result, which is take window size, usual window size, classical ones. You have an error that goes to 0 uniformly on the support with a rate which is the square root of the classical minimum maximum. And if the dimension is less than 7, you are also not uniformly, but pointwise equivalent to the classical kernel density estimation. So here, you lose nothing with the estimation of the support when the dimension is less than 7. So I'm going to try to explain why this awful formula works and where the 7 comes from. I think it will be okay. Okay, so there is a lot of other results on the maximum, etc., etc., etc. We'll go there after. I just want to show you a little bit how the proof works, and maybe you can see if you see that if it is possible to adapt to the dependency case. So the first point, if you look to the indicatrix here, at least you can truly put the good hypothesis in your model so that the probability that the volume is too small or there's too many points on the boundary goes to 0 as fast as you want. It's not a problem. And let's go here. So you use this decomposition of the error. And the first one deals with the number of points that fall in the boundary of the convexure or inside the convexure. And this is the fun part, where the independence hypothesis is required, I think, for what to deal with. This part, which is mostly purely geometric, not so fun. So the really fun one is this one. And it's come from a paper, so a paper of Berlin and Rice. You say what I'm going to do. I can do what I am going to write. And it is possible to deal with that. We are authorized to condition. And if we do that, we can know exactly the law of that. Imagine you have points, and endpoints, and you know your x here, and you know the convexure of the point that in this small ball. So what do you know? If you know the convexure, you know the vertex of the convexure. So you know the location of n boundary points. So it remains little n minus this n boundary points, which are random. And the probability to have a binomial law of parameters n delta is there. And the probability is the probability to fall in the probability contents of the convexure, which is and this one, you call this one. And so if you have that, you clearly have that the mean of this variable will be 0, and you can have really easily points on the values. The only point here is to see that, and then you do some calculus, and there is no more. And it's here that you require the independence hypothesis. I don't know. I really don't know. Just know of the dependency, but I don't know if you can do things like that. Yes, you can apply the same formula in the field. And the other part is really solved. It's clearly very easy, and it's mostly purely geometry. And sometimes, if you want to be not too rough, you have to use result of Victor Emmanuel Brunel. But mainly, if you look to the second part, this one is just that. One part of the error is this one. And this one, everywhere, just using the C1 thing of F, and also the geometry of the support. You also need the rolling ball condition to have this one, which is always a big toe of Rn. And if you want to be a little bit tricky, you can look at what happens inside. and inside a bit more less rows, and you can manage to make appear the volume of it. Yeah, no, it's right. You make appear the volume of what is not catched by the convection. Yeah, like this one. Yeah. And what happens is that when the function is less than 7, those 2 zeros quickly enough to be neglectable with regard to the overrest. When you are in higher dimension, you feel less the convection, and this one explodes, and it's this kind of answer that makes it's a problem. But with yeah, I think this part is really adaptable to the dependent case with same kind of results that the one I showed for the support part estimation. What? I think. Oh yeah, it allows a lot of things, because if you have that and you have regular line, you can also have a classical result of level set estimation and B minimax. When you have a level set far enough from the boundary and convergent for every level set, which is quite an improvement. And doing that with just, I think it's a last slide I'm going to show. Doing not exactly what was proposed in the initial paper, but doing this, which is just a small inversion of step. First, you make a filter, you just take the observation which has a large enough density, then you make the local conjecture estimator of this subset. So you don't overestimate the subset too much, as it was done in the original paper. So it's a proposition of improvement, and I think with the that's refinement. Okay, and that was nice, but I think I'm unable to see anything here. You are unable to see anything here, which so if you want to see it on the computer, it's possible if you're interested in, which is the plot done with the initial method and the one with the corrected method. And so you can see that this one is a bit less messy, and the set are more small. But here you cannot see anything. So it was just to say, oh, look, my method is there, but look, nothing. Okay, this last one. So what else? There is an idea of really using reasonable instead of fixed radius. Looks a good idea to be more adaptable to local difference. Bad point is that you lose a bit of robustness, and the very bad point is that there is a tricky step of depositionization, which make me a bit crazy this time. The good part of such method is that it's really easy to adapt local PC or prediction or true function space if we are non-manifold estimated total plate if we have an unknown manifold, but it's really easy to adapt when in fact your points don't lie in Rn, but in some manifold of Rn. So it's just a small step of prediction. If you do it not turn too badly, you can have estimation on manifold. And by the way, it is exactly what has been done here, because the Earth is a manifold. It's not a map, and just not to have thinking like that. So thank you. Right.
Any questions?
For instance, what can you say when there is when the dimension is high? Does it work?
It's still convergent, but you do not achieve minimax rates. So what you will give the rate is this one is really how do the little convection estimate the true the true thing. The true thing is what you get to catch is the intersection between the support of the ball. How quick is this filling done? So it's clearly converging, but it converges very slowly. It's this rate that will be put. Exactly, that will be RN you will have this term that you can neglect when they is small. Small. You will have the max. You have the classical this one, and so the classical one in density estimation are this one and this one. If you take the RN, which is the minimax one, actually this one can be neglected, but the rate with in any dimension is given by that. So you can minimize, you can find something that goes to zero, that minimize.
Maybe I just spent the recording, but
Adobe Acrobat Reader ou c'est un autre truc
c'est le truc de base.
Ok, parce que peut-être que j'ai des animations qui vont peut-être pas marcher. C'est pas grave.
Ok, bah, écoute,
Attends, ça on va l'enlever parce que c'est chiant. Masquer les corps. En fait, ça marche? Ouais. Parfait.
So you have 5 minutes for the talk, that's it.
You staying here or
Oh yes,
you don't
yes.
want to sit there?
No, because
It would be better. Anyway.
Ok.
Tu veux que j'attende?
Ah, si, vas-y, c'est bon. Non, non, c'est bon.
Okay, so I think it's the last talk for today, so I'll try to keep it relatively short. So I'll be talking, well, actually, it's funny because usually I talk about convex cells, but it's been done, so I'm not going to talk about convex cells. What I did in the last Econet conference, I thought I would talk about something new. It's not directly related to network inspection, but it's definitely related to ecology. Although it doesn't show you the title, but you see the link. So this is a joint work actually with Carlos Salina and Pierre Valois. But if I have time, we'll see. I'll talk about two problems, but actually two. Well, one of them is the full model for the problem we want to consider, and the first one is a simpler version of it, which is the one we managed to solve. Okay, so let me present this first passage problem for the Brownian supremum. So that's when there is a connection with ecology. Animals, maybe I'm not. So we have an animal that's foraging for food, and we're modeling the motion of this animal by a Brownian motion. By the standard, is also like a general Levy process. There's a whole literature, obviously, on animal motion, animal movement, and models for that. So we take this very simple model. And the idea is that there's on this, so it's a one-dimensional animal in a it's a zero-dimensional animal in a one-dimensional world. And in this world, there is, that's like theoretical physics. And in this world, there is 1 unit of food per unit length. No food replenishment, so when the food is eaten from one place, that it's not replenished. And the metabolism of the animal is very simple. It needs 1 unit of food per unit time to survive. and it can stockpile an infinite amount of food. So there's no limit. It won't need an infinite amount, but there's no limit to what it can stockpile. And we ask this very simple question: what is the survival probability of this animal, this zero-dimensional animal in this one-dimensional world? We start by the simpler version when there's food only on one side. So your animal lives on the verge of a desert. Then there's food just on one side. On that side, there's no food. Then you can see easily that actually, if you look at the maximum of this Brownian motion that models the motion of the animal, the movement of the animal, then the amount of food that's been eaten at a given time is actually the running maximum of your Brownian motion. It's the territory that's been explored on the positive side. So it's exactly when there's 1 unit of food per unit. We could actually add a multiplicative constant like A times, which would be the number of units of food per unit length. But here we've taken A. So we have just this relationship, and then the survival probability is simply the probability that the running maximum is always larger than the elapsed time. As long as it is the case, the animal survives. And as soon as the maximum becomes less than the elapsed time, so as soon as the maximum hits the diagonal, the animal dies. It's eaten less food than the elapsed time, so that's what it needed to survive. So our very simple question is, can we compute this probability of the density for this random vector? Tau is the random variable when the maximum first hits the diagonal for the first time, and we want the PDF for this. And so the survival probability would just, the PDF for this would just be the antiderivative or minus the derivative of the probability that the max always remains large, the running max is always larger than the elapsed time. And we just want to compute this. So afterwards, I'll actually show you, or mention 2 ways of computing this using other methods, but let me try and keep things simple because I do only simple math. So I tackled this problem using simple physics intuition, and then we made it regressively. It actually works, so it's nice. So the idea is to look at paths that have, okay, m of t equals t, but that's t plus or minus dt of t, otherwise it would be 0. So the idea is to say, okay, if the animal dies at t because its max at t, its running max is equal to t. Okay, that's true, but if you look only at paths that have m of t equals t, obviously you're over-counting because there are paths that have m of t equals t, but actually m of s equals s before. So they could have had, this path, for example, it has m of t equals t here, but it has also m of s equals s here and m of s equals s here. So it actually, if you look at this path, it actually died even just at the beginning here. So if you just naively look at these paths, obviously it's wrong because you're just grossly overcounting. Then, yeah, I want to minimize. Yeah, thanks. Then, but still you can exploit this idea by saying, okay, then I'm going to compute the PDF for the paths that I'm interested in by looking at the PDF for the paths that have m of t equals t, but I want to subtract all those paths overcounting. So that is all the paths that have m of t equals t, but also m of s equals s for some s less than t. So if I manage to compute this, then that's it. I get the s I want because obviously this is easy and this is known. This is just just get a PDF for m of t and you equals t. So yeah. Maybe for time it's going to be a very short talk because that's anyway. So the idea again is to try and do as few computations as possible. So I'm going to find a path transformation so as not to have to compute this complicated PDFs. And so I'm looking at a path that has m of t equals t here, but it has already died before. So let's say I take the S, which is larger but not equal to t, for which you have already m of s equals s. In my case, in this case, I'm going to look at this s here. So at this time s here, you have m of s is equal to s, and the path is actually diagonal. And I'm going to transform this path so that I can count its probability between this path in an easier fashion, easier manner. And the basic idea is I'm going to use the excursion, downward excursion that is here. So let me just first convince you that there is downward excursion. But if you have m of s equals s to some s strictly less than t, it means that here, so this level is s, okay? You know that m of t is equal to t, so you know that you're going to cross this level again. So this, there is a time after s, but before t, strictly on time. There is a time when you cross the level m of s, which is just s again, because you know that you're going to reach t, which is strictly larger. So this time is well defined. Also, tau 0 is well defined, because say that this is a condition on the fact that at s, your maximum is equal to s. So there is a time tau 0 before s when you actually hit this level s before. So here you do have a downward excursion below this level s. And the whole idea of the path transformation is that is to use this downward excursion because you see immediately that you can extract it from the path, slide the remaining path from here to the end and slide it here. You don't lose anything about this path that has a maximum equal to t. And then you have this excursion, you can extract it, you want to do something with it. You still want to have a path that has a duration equal to t. And the simple idea is to do something that is bona fide transformation, you want to do. And you transform your path into a path that has no constraints apart from a simple constraint of which you can compute it. So that's what I said, it's a downward excursion, and we want to extract it and use it. And the way we're going to use it is actually, we're going to use it to basically lift up the end of the path. So that we'll be able to say that the path we get after the transformation, it has duration t, but its maximum is larger than t. And what we want is that there is no constraint on this path, apart from having a maximum that's larger than t. And then we just need to use the PDF for running path duration t to have a maximum well, probability for running path for max larger than t. So we just need to see how we can transform this. So to do that, I need to define two more times. Well, we have already s, and we have already tau 0, we have s, we have delta. So I need just one more time, which is tau star, which is the time at which the initial global maximum, which is equal to t, is obtained the first time, which is after delta construction. So I define this time tau star, and then that's when we see whether the animation is going to work. But it looks like it's not going to work from what I see here, because it's probably not the same. Let me see actually. Yeah, it's not working on this because it's not Acrobat Reader. Anyway, okay, so I'll try to explain it like this. So the path below is the original path, and the one you see above is the transformed path. So what I do is I take this excursion and I transform it into what's called an upward first passage bridge by splitting it at time s, flipping upside down the first part, the blue part here, and just lifting up the orange part that is after s. Okay, this is a standard transformation. You find it rigorously defined and studied in this paper by Bertrand Chaumont in 2003. And so now you see that I've gained some height. So it's definitely going to be actually you have this part which you've gained some height from here. And you can say how much height you've gained because you see that there the excursion was split at time s. And in fact, when you transform, you're going to gain twice the difference between the level below which there was the excursion. So the difference between this level and the height at which the motion was at the splitting point, S. So this is S minus BS, in fact. So the height I will gain is going to be 2 times S minus BS. Okay, but anyway, I gain some height, and then you just, the green part here, that was the part after the excursion, that took you from level S to level T. You slide it forward in time here. Then you put your first passage bridge, and then you put the remaining part, which is just going below, which is just which was descending, decreasing from the maximum here. So you will be decreasing here. So you know that the maximum is still attained at the same time, but now its height, the value of this maximum, it's no longer t, it's t plus some positive constant, and this positive constant, as I told you, we know what it is, but constant, it's not a constant, it's a random value, it's s minus bs, 2 times s minus. We actually know by how much we decrease here the maximum. Of course, you need to check that all the things are rigorously defined, the times are defined, and that's just one side of the transformation. You want to see in fact that we have a bijection. So you can check that when I skip the details, but starting from a path that has a maximum larger than t, you can actually identify points and cut your paths at these points and then move things around and stitch things back into a path that will be exactly the path that has a maximum equal to t, but it has a maximum, a running maximum less than the elapsed time and some time before. So we have path transformation both ways. So what we've shown with this path transformation is that actually let me get to here. So we've shown that the paths that have m of t equals t and m of s equals some s less than t, these paths are actually equivalent, this set of paths is equivalent to the set of paths which are just m of t larger than t. And this we can compute easily because then we just need to integrate the PDF for the max of the Brownian motion from t to plus infinity. So it's just integrating this PDF. And we get this, which we can check, of course, if it's density, etc. And if we want to check more than just by seeing that it's a density, you can actually derive this density. You can derive it using other methods. One way is to look at the reciprocal process of m of s minus s. So m is the running maximum of the Brownian motion. You get m of s minus s. It's a spectrally positive Levy process. You can use some machinery associated with that to compute the first passage time of that 0. Or you can also, without using this machinery, you can work your way around the proof by using another fact, which is that m of t minus t is distributed like the Sorgen time with 0 of b of t minus t. This is very much like an Artin law, actually. And using that, you can write down a longer proof of the same thing. The first technique was used by Dooney in 91. The second one by Imhoff actually in 86, or maybe it was, yeah. But the thing is, with using the path transformation, as I told you, we keep track of the value of B when the Brownian path dies. So we know by how much it's we lift the path in the path transformation, and using this information, we can actually, putting in some more effort and some work, we can actually get the joint flow, the time when the maximum hits the diagonal, and the value of the Brownian motion at that time, which is obviously below the max, but we don't know what it is. But actually, we're able, but with the previous techniques, we didn't know this. Now we know the joint law for T and BT, and we get it with the path transformation. I still have some time, even if I want to. 2 minutes if I want to do no, 2 hours, just 2 minutes. 2 minutes, I said that do 20 minutes. So in the last 2 minutes, I can, and it's not going to last more than 2 minutes. So if you come back to the original problem with food on both sides. Then what you want to look at is the range, between the sub and the mean, so the running max and the running mean. And well, that's all I'm going to say because it's an open problem. I've been working on it with Pavo and Pierre and still haven't found a solution. We're working on it for a couple of years now, but we're still trying to derive something like that. Our minds are nice and interesting problem. Well, there's many things to apply, and of course, it's not the same as before because you have to keep track of both sides. You cannot use the simple part transformation as the one I used for Max, where you basically don't care about what happened below. So you transform your path, maybe lift it, you go further upward, and you don't care about what happened downward. With the range, same, you have to keep track of what happens on both sides. And yeah, that's about it. So we're trying to use the same idea because the first part is known. It's just the PDF and the range. You can use the same reasoning as before, but we still haven't been able to do that. And I'll stop there. If you want to see the paper, it's in stochastic processes and verification. It's just come, well, it's come online a few months ago, and now it's fully published. Thank you for your attention.
Is there any questions? Maybe.
The second problem you said you cannot compute the density.
Look, we have the density of the range, which is known with the density is actually the this is in the Feller, the paper by Feller. So you can compute the PDF and the range to be.
So what is open? I mean, what's the
So that I think we cannot compute the density for the time when the range becomes less, when the running range becomes less than the enough time. This is not
how much do people do you think will get the problem if you use another processing approach?
Yeah, no, that's a good question. The path transformation work. Well, we need. The thing is, we're using the continuity of paths. So it's going to get. I don't know how much more difficult, but difficult.
Because if someone's interpreting that they have the ecological models, we cannot problem at their issue.
Yeah, with the yeah, I haven't heard about, but I haven't worked on it because we're focusing on the range. So that's something we're trying to do.
Okay, so I think we should just stop. And I wanted to tell you because tomorrow there is one COVID case in the lesson, so I wanted to get the change and to finish just at 1 p.m. So let me just do it. So I wait. I just stop recording first.